This video is part 2 of a discussion of the Attribute Capability Analysis Statlet added to Statgraphics 18. Part 2 describes Bayesian methods. The Attribute Capability Analysis Statlet uses both classical and Bayesian methods to estimate either the proportion of nonconforming items or actions or the rate of nonconformities. Part 1 of these videos described classical methods for estimating a proportion or a rate. This part describes Bayesian methods of estimation. We'll begin with estimation of a proportion. Let's suppose that we inspect a random sample of n items and classify each item as either conforming or non-conforming. We'll let x be the number of non-conforming items in the sample, and theta be the proportion of non-conforming items in the population from which the sample was selected. For example, suppose we inspect n equals 100 items and find no non-conforming items. How should we estimate theta? If the n items are randomly sampled from a population, then x follows the binomial distribution shown here. The Bayesian estimation approach begins by constructing a prior distribution describing our knowledge about theta before the data are collected. We combine the prior distribution with the likelihood function of the data to create a posterior distribution. We then use the posterior distribution to find point and interval estimates for theta. For data that follow a binomial distribution, the conjugate prior distribution for theta is the beta distribution. A conjugate prior distribution is a distribution which, after combined with the likelihood function of the data, yields the same form of distribution. The beta distribution is defined by two parameters, v and w, and can take various shapes as shown here. In order to use Bayesian methods to estimate the proportion of nonconforming items, we need to select our prior distribution. In the case of the beta distribution, that means picking the values of v and w. One way of doing that is to assume that all values of theta are equally likely prior to gathering our data. A uniform beta distribution is defined by v equals 1 and w equals 1. A second way to select the prior distribution is to use the posterior distribution derived from a previous analysis. We could also specify the mean and variance of our prior knowledge about theta. The values of v and w would then be derived such that the beta distribution has that mean and variance. A fourth and final way to determine the values of v and w is to specify two percentiles of the prior distribution. For example, we might specify the 50th percentile and the 90th percentile. To analyze our particular example, I've loaded Statgraphics 18. I'm now going to go to the top menu and select Statlets, Statistical Modeling, Process Capability Analysis, Attributes. This will open up a Statlet window. The parameter I want to estimate is the proportion of nonconforming items. The method I'm going to use in this video will be Bayesian rather than classical. In our data, we observed 0 nonconforming items out of 100 sampled. I'll ask for 95% upper Bayesian limits on theta. By default, the program assumes a uniform prior distribution for theta. You can see up here on the Statlit toolbar that the two beta parameters begin at 1. After combining the prior with the likelihood function of the data, the posterior distribution, which is also beta, has v equals 1 and w equals 101. The graph shows that posterior distribution. The Bayes estimator of theta is given by the mean of the posterior distribution. In this case, that's slightly less than 0.01. The 95th percent upper bound on theta is given by the 95th percentile of the posterior distribution. It's slightly less than 0.03. You can also see the calculated values of DPM and other capability indices at both the Bayes estimate and the 95th percent upper bound. I talked about these quality indices in part 1. If I want to specify something other than a uniform prior, I'll go to the Statlit toolbar and press the button labeled Set Prior. I can specify either the mean and standard deviation of my prior knowledge about theta, or 2 percentiles of the prior distribution. In this case, I'll specify 2 percentiles. I'll specify the 50th percentile, which I'll set to 0.005. That's about 1/2 of 1%. And the 90th percentile, which I'll set to 0.01. When I press OK, it'll now redo the analysis using the beta prior, and it's determined, given my percentiles, that V is about 2.9 and W is about 519. You'll notice that in this case, specifying prior knowledge about theta has reduced substantially both the Bayes estimate and the 95% upper bound. We can do a similar analysis if we wish to estimate the rate of non-conforming items. In this case, let's suppose we've inspected a span of n units, where units might represent items, time, space, or some other quantity. Let's let x be the number of nonconformities in the sample, and lambda be the rate of nonconformities per unit in the population from which the sample was selected. As an example, during the years 2000 to 2014, U.S. air carriers flew a total of 88,727,394 flight hours. During that period, there were 3 fatal accidents. How should we estimate lambda, where lambda is the rate of fatal accidents per flying hour? If we assume that accidents occurred randomly over that time period, then x follows the Poisson distribution shown here. For data that follow a Poisson distribution, the conjugate prior distribution for lambda is the gamma distribution. The gamma distribution is defined by 2 parameters, alpha and beta. You can see here different shapes depending upon the value of those parameters. As before, we can set the parameters by specifying either the mean and standard deviation or 2 percentiles of the prior distribution. Now let's analyze our data. I'm going to go to Statlits, Statistical Modeling, Process Capability Analysis, Attributes. The parameter of interest this time will be the mean rate of nonconformities. The method is Bayesian. The number of nonconformities is the number of fatal accidents, 3. The sample size is the number of flying hours, 88,727,394. Again, I'll ask for 95% upper Bayesian limits. In order to set the prior distribution, I'll specify 2 percentiles. The 50th percentile I'll set to 3 e to the minus 8. The 90th percentile I'll set to 5 e to the minus 8. I'm saying here that I'm 50% certain that the accident rate is less than 3 accidents per 100 million flying hours, and 90% certain that the accident rate is less than 5 accidents per 100 million flying hours. When I press OK, the results will be displayed. Based on the posterior distribution, the Bayes estimate of the accident rate is 3.25 accidents per 100 million flying hours. The 95% upper bound is 5.27 accidents per 100 million flying hours. I talk more about Bayesian estimation of proportions and rates in chapters 2 and 3 of my book, Process Capability Analysis, Estimating Quality, published by CRC Press.